Okay, this is Unit 8, Kinetics and Equilibrium, Lesson 1. In today's lesson, we're going to talk about collision theory and factors that affect the rate of reaction. Kinetics is the study of the rate or speed at which reactions occur. A reaction is the breaking and reforming of bonds to make entirely new compounds. Breaking and reforming of bonds to make entirely new compounds. And a reaction mechanism is a step-by-step process needed to make a product. So basically how you get from point A to B. It's kind of like a recipe. Reactants to products. Now normally when we look at an equation, say we have A plus B yields C. We really think that that's all there is to an equation. But there's usually multi-steps or several other steps that we don't see that are going on behind the scenes. Just like when we bake a cake, we must follow the directions. You can't omit any steps. You can't change the order of the steps, and you can't omit any of the reactants or ingredients, or it just won't turn out right. And it's the same thing with a chemical reaction. Determine whether each of the following chemical reactions is an example of a slow or fast reaction. Explain why knowing this relative rate of reaction is significant. Well, let's think about rusting. Is rusting a slow or fast process? Hopefully you said slow. Alka-Seltzer and water. We've done that lab already. You know that that pretty much goes fast. Styrofoam decomposing. Now when we talk about styrofoam decomposing, we're not talking about styrofoam and acetone. We're just talking about styrofoam in nature, and that would be slow. Weathering of rocks, that's slow. And bleach removing color, well, that goes pretty fast. So why is knowing the relative rate of a reaction significant? Well, basically, rates of reaction determine everything from an explosion to how effectively you digest your food. For example, if you just eat a meal, it pretty much digests carbohydrates pretty quickly, and your blood sugar goes high from the carbohydrates, and then you crash usually. However, if you add 2 tablespoons of vinegar, so like let's say you eat a meal and you have salad with it with 2 tablespoons of vinegar. The vinegar acts as an inhibitor, and it slows down the rate of the carbohydrate digestion, so therefore you have a more even blood sugar than you would without the vinegar. Well, in chemistry, we're going to study reaction rates and mechanisms to determine how a chemical reaction reaches equilibrium. So what determines the rate of a reaction? Well, there's a number of steps. The more steps can mean a slower reaction. The rate determining step is the slow step of the reaction. So I want to make it perfectly clear. Just because you have something that has a lot of steps doesn't mean that it's necessarily going to be slower. For instance, I could ask you to leave my room and go to 15 different rooms in the high school and collect a piece of evidence. So that's 15 steps. However, I could ask you to go to the cook school and pick up a piece of evidence, which is only one step. So 1 step isn't necessarily faster, and 15 steps isn't necessarily slower. It really depends on what's going on. So here I have a reaction. This is called the overall reaction, this top one. And then I have 2 subsequent steps that happen to make this overall reaction take place. So we have step 1 and we have step 2. And step 1 is the slow step. So this, remember, is the rate determining step. So if we were to look at this reaction, A plus B going to the top of this peak, this is step 1. That's your slow step. And then AB plus C going to here, this is a fast step. This is step 2. So what we can see is that step 1, what's called this reaction pathway, it's longer. So the reaction pathway is longer. Meaning it takes the most time. This right here is more time to get there. It's like riding a bike up a huge hill. It's going to take longer. And this longer step, which is the slow step, as I said, is our rate determining step. What determines whether a reaction takes place or not? Well, there's a couple of things. In order for a reaction to occur, reactant particles must collide. And they can't just collide haphazardly. They have to have the proper amount of energy, and this is called EA. We'll learn about this a little bit later on, activation energy. And the proper orientation. Sometimes this is referred to as bond angle. Or direction, a couple of different words. So here in A, you see 2 particles begin to collide, and they collide with the right amount of energy, and then something happens. The reaction takes place. Only when particles collide with these 2 conditions being met will there be an effective collision resulting in a reaction. There can be lots of collisions, but if you don't have the right amount of energy and you don't have the right bond angle, it's not going to be effective. Let's take a look at a little video.
We'll color the H2 molecules red and the I2 purple. Let's watch them as they move. Was there a reaction? No, there was no reaction. Why not? The basic idea, or the basic premise, of the collision theory is that in order to react, molecules must collide. And as you can see, they didn't collide this time. So does that mean they'll react every time they do collide? Okay, let's watch these molecules as they approach each other this time. This time they did collide, but they didn't react. They bounced off each other unchanged. So why didn't they react? Well, it's because they didn't have enough kinetic energy, or energy of motion. In order to collide hard enough to cause a chemical reaction, that, by the way, is called a successful collision. Particles must collide with a certain amount of kinetic energy. The minimum kinetic energy particles must collide with in order to have a successful collision, that is, result in a reaction, is called the activation energy, or EA. Having anything less than this energy, they will not have a successful collision and there won't be a reaction. Having this energy or greater will give them a successful collision. Let's consider this collision, this time with a little more kinetic energy. When the particles collide with enough energy, they form an unstable combination of atoms. This is called the activated complex, and in this case it has the formula H2I2. If they collide with enough energy, the bonds in the H2 and the I2 will break. And then what happens is new bonds will start forming between the H's and the I's. Now what happens is the new HI molecules, called the products, start moving away from one another. So the chemical reaction is now complete. The two new products, two molecules of HI, have now been formed and are stable. We can summarize this whole process now. The reactants, H2 and I2, collide to form the activated complex, H2I2, an unstable arrangement. The activated complex then breaks up to form the products, two molecules of HI. Okay, watch this collision between H2 and I2 molecules. Was this collision effective? No. Why not? Well, let's take a closer look. Notice how the red H2 molecules are oriented in space, like that. When the molecules collide, the red H2 molecules are not oriented in the correct way to form the activated complex. They're not lined up the right way. Recall that in order to form the activated complex, they should have been oriented this way, so each H can hit an I. In this case, they form the activated complex, and this is called a successful collision. But that's not what happens in this collision. We can say that these molecules do not have the proper orientation for a successful collision. We can also say that they don't have the proper collision geometry. One more term we can use for this is alignment. We can say the molecules don't have the proper alignment for a successful collision. So we can now summarize a collision theory. The three requirements for a successful collision. The first one is the molecules must actually collide. They can't miss. The second one is they must collide with sufficient kinetic energy, greater than or equal to the activation energy. And the third requirement, they must collide with the proper orientation, alignment, or collision geometry. In that case, there's no reaction because they didn't have the proper collision geometry. In this one, there is a reaction because they did.
What are some factors that affect the rate of a collision? Why is it that certain reactions go faster than others? This can be explained by 6 factors that affect the rate of reaction by changing the number of effective collisions that take place between particles. The more effective collisions, the faster the reaction. So, nature of the reactants, meaning what type of substances are we dealing with? Well, ionic substances react faster. Why? Because ionic compounds generally have less bonds. NaCl, MgCl2. So less bonds to break means less steps. Whereas covalent, or remember that means molecular, substances react slower. Why? Because generally, if they're covalent, they're all nonmetals and they're much larger. So they have more bonds to break, which means more steps. So let's look at the two examples. Here I had NaCl and AgNO3. Well, all we have to do is break one bond between Na and Cl and break another bond between the Ag and the NO3, and then the Na hooks up with the NO3 and the Ag hooks up with the Cl. Whereas down here you have methane plus oxygen yields carbon dioxide and water. We have 4 CH bonds to break because this is CH4. These are all H's. So we've got to break 4 CH bonds. We then have to break one OO bond. And for the water, we have to break 2 OH bonds. And for the CO2, which looks like this, we have to break 2 CO bonds. So you can see that there's a lot more bonds to break in a covalent compound with a reaction taking place than ionic. So that's nature of the reactants. Next one is concentration, which should be numbered number 2. Increase concentration, we increase the reaction rate. Well, think about it. The more particles you have per unit volume, the more chances are that something's going to collide. Versus the less concentration, there's less particles per unit volume, so fewer collisions. The more particles in a given space, the less space between particles. Therefore, more collisions. Pressure. Now, pressure only affects gases. Increased pressure increases reaction rate, and gases only. So if I increase the pressure, then that decreases the volume, which then decreases the space between the particles. If there's less space between the particles, then there is more collisions. Temperature. Increasing temperature increases reaction rate. You know this, we've already talked about it. If you increase the temperature, particles move faster, so there's more total collisions. Therefore, there's greater average kinetic energy, and collisions take place with more or greater energy. Surface area. Increase the surface area by making the pieces smaller. Remember that. It's an opposite. This increases the rate of reaction. Think about a cup of hot tea. I've got a sugar cube. I've got granulated sugar. Which one's going to dissolve faster? The granulated sugar. Why? Because it has more surface area. That means that the solvent has more contact with the solute surface. Whereas a cube of sugar, it has to work its way in. It's got to remove the outer layers before it can get to the inside. So increasing surface area exposes more reactant particles to possible collisions. And 6, a catalyst. A catalyst speeds up the reaction without changing the nature of the reactants and or the products. It provides a shortcut, if you will, or alternate pathway. For the mechanism. And it does this by lowering the activation energy for the reaction. This is extremely important. It's on every Regents exam. You have to know what a catalyst does. You have to know how it does it by lowering the activation energy, and you have to know that it does not change, okay, without changing the reactants or the products. So in this reaction right here, if this was my reaction, and let's just say these were my reactants, these were my products, this is up here what's called the activated complex. We're going to discuss this in more detail. This is that intermediate stage. The activation energy is this amount that it takes to get from the reactants to the top of the hill. If I put a catalyst in here, this would be a catalyst right here, you can see that it lowers the activation energy, and now it takes less time to reach the top of the activated complex. So this is the amount of activation energy without the complex. This right here is the activation energy with the catalyst. So I'm going to show you two demonstrations. The first one is the elephant toothpaste demonstration. I usually do this demonstration for you along with the genie in the bottle demonstration, except for somebody finished all our 33% hydrogen peroxide. You cannot use 3% hydrogen peroxide, which is what's in the store.
Knows how to make learning fun from Littleton, Colorado. Please welcome science guy Steve Spangler. So, all right, what are we doing?
Okay, so I think the first science experiment anybody ever did was maybe breathing helium. You know what I'm talking? So you breathe helium and your voice
I gotta tell you, I never took science class, I swear. I never did.
Okay, so this is your first science class.
It is.
So this will be fine. All right, so you breathe helium and your voice goes really...
Yeah, I've done the balloon thing. Yeah, hi.
Right.
Yes.
So
And
I was
is
thinking...
that okay to do to your boat? Is it safe? Is it dangerous?
We always say, don't try this at home.
Okay.
Try it at a friend's home.
Okay.
So if you... So, I mean, that's the legal thing.
Okay.
All right, so helium is 6 times lighter than the air we breathe. So I was thinking, what if we used a gas that was 6 times heavier than the air we breathe?
It'd be different.
Yeah, so here, watch this. So, see, that's already good. You did a good job.
Right.
So here we go. So you just put a string onto this. So this gas is 6 times heavier than the air we breathe. And I'll show you. Oh, that tricked me for a second. All right, so here we go. Watch what's going to happen. So what I want you to do, I'll teach you how to do it. You're going to breathe all your air out. You're going to go. And then I want you to breathe in half the balloon, and then just talk to the audience. Okay, ready? Keep going, keep going, keep going. Okay, now talk to the audience.
All right, I will talk to the audience.
Yes.
Luke, I am your father. Is that right? No, really? That's really weird. It's totally, you okay? Yeah. Breathe it. The only problem is it'll stay like this for about 3 weeks. All right, so... What's going on in my life?
So breathe in, ready? Now breathe out. See? You're good now. Try it again.
I hope I am.
All right, see, you're good.
I think so.
Okay, you're good. All right.
This is ridiculous.
All right. See, but now this kind of makes science fun. I always tell teachers, if it gets to the dinner table, you win. You know what I mean? So kids talking about that. If a science teacher's doing that,
What is this called?
it's called sulfur hexafluoride.
Okay.
Yeah, it's not a big deal. It's okay. It's perfect.
Yeah.
All right. So safe science. Wear your glasses.
All right.
All right. So here, this is kind of fun. So when you got a cut as a kid, you would always put on, Mom would always put hydrogen peroxide on. You know that stuff.
I wish they would have done that for me.
So this is just like really concentrated hydrogen peroxide, and it's got see a little dye in there in the bottom. So this should be perfect. All right. You really only need about 3 drops, but I was thinking for a big show, why not? All right. So here, this is your part. You squeeze in some soap.
Okay.
So put in
How
some
much?
soap. Just. Oops, that's too much.
Okay.
All right. So no, it's fine. Just a little bit more.
Okay.
Okay, good. And now let's squirt a little bit in this one here. We're set. Okay, good. That's perfect. Now, this over time, the reason why people keep that hydrogen peroxide in the refrigerator is to keep the oxygen from coming out.
Okay.
So this stuff right here actually makes it come out really, really fast. All right. So this is this catalyst that's going to flood. So when we pour this in here, my only suggestion to you is that God, no. That's bad. Man, that was really bad.
I see something in a shot glass.
No.
What do you do?
No, that's not a shot glass. That's a very scientific.
I was going to put it on my belly button. I was going to have you. All right, what do we do?
All right, so now, when I say go, you pour it in there and then stand back. Fast. All right? Ready? Here we go. 3, 2, 1, dump it in, and stand back if I were you. Wow. Is that cool? I just can't get it to stop. It just keeps going.
Wow.
All right?
That's amazing.
That's cool.
Wow.
This looks really good, but I take
Take
them
them
off.
off. All right, let's take them off.
Right, so here, this last little bit.
amazing.
Isn't that kind of cool?
Yeah.
So all the oxygen comes out, and again, kids are talking
So
about
that's
it.
just all oxygen that comes out.
Yeah, and one of the problems is that teachers just don't have time nowadays to do all the science that they want to. So parents can kind of get into it. It's not hard to do. So here, I'll show you a toy that was a lot of fun. So if I say William Tell to you.
Okay, so that was the toothpaste demo. Again, I'm sorry I can't do that for you since I don't have any 33% hydrogen peroxide left. And the other one that I wanted to show you, which is very similar, is the genie in the bottle, both also operating to use a catalyst. Here's the other one.
Mark wants 3 more wishes.
This genie is so special, Mark, that you got to put safety glasses on. It's not often that a genie...
fiery genie.
No, just a genie inside. So here, so watch this. Oh, great genie, come out of the bottle. And you can just see...
Nothing.
Yeah, I know. Get out of it. I will bring the pod. All right. Oh, we have to uncap it because it is a lazy genie.
Okay.
So here's old great genie. Let's see.
Oh,
great. Oh my gosh. Would you look at how great. Wow. Smells a lot like a genie too. Wow, bottle's getting warm. Mark, viewers have said I tell you the secret too quickly. So it is I set up one for you. There's a genie inside.
Right.
Honestly, there's not chemicals. So there's just a genie inside there. So you open it up, and then I'm going to let you guess how it works.
Okay.
Fair enough? All right.
This one?
So, oh, great genie.
Oh, great genie.
Very good.
Please exit the bottle.
Toy Story made 130 million.
130 million this weekend.
Somehow.
And nothing.
No, the genie had to be rustled just a little bit. Right?
Oh.
Yeah. Maybe we got.
My genie's rushing.
Did not grant you as many wishes.
Oh, there you go. There it is, though. Oh, how
Isn't that very,
cool
very pretty?
That is so
a
cool.
special effect artist will will use something like that. Honestly, the burning sensation in the lungs goes away after a while. So that's
It's a little pungent.
that's a little, yeah. Genie needs to take a shower. That's all right. So I'll give you a little secret. There's a chemical down inside. Any idea what that is?
It's obviously not nitrogen or
No, because it's warm. So
Yeah.
the viewers can't really, and you'll be able to see it here in just a second. Take a look at
Is
this.
it sulfuric acid?
No, because it'd be a little too dangerous. But it's not like this isn't dangerous. Mom used to use something like hydrogen peroxide.
Hydrogen peroxide, right?
So and it's 3%. So you go to the store and you get that, and it bubbles on your skin. It means it's releasing oxygen. Well, this is 30%. So so you'd get burns on your skin if you even touch it. So you have to be very, very careful. But let me show you how we put the whole thing together. All right.
All right.
So if you bring over the clear bottle, we'll show the viewers how we do it. So first of all, we're using the 30% hydrogen peroxide, and we've got to release the oxygen from there. And so we want that, and we're going to have a little bit of that steam or that vapor that's going to come off as well. So there's our 30%.
Right.
And then the next part here is called a catalyst. And so if you look here on the table, it's a black powder called manganese dioxide.
Oh, sure.
And
I've
a
seen that before.
catalyst is something that that is not consumed in the reaction. It's just used to kind of speed along the reaction. So I put some of that manganese dioxide here in this little piece of toilet paper or tissue paper. All right. So now this was hanging on the bottle like this, and you didn't see it. And then there was a little cork that was here, and I cut off the string. See?
So the minute you release
You
the
got
cork,
it. So as soon as you do release the cork, that falls down inside, and you start
and
to
there
see
it
the
goes.
reaction.
Look at that. There
Isn't
it
that just
is.
beautiful?
Sure
And the little
enough.
genie comes out.
There
So a lot
it
of
is.
special effects, and today kids need to know something about that science isn't just a lab coat and a guy in a bow tie, and that whole thing. There really is. It's something that happens in the movies.
Yes, this
and
makes
there's
it
other
so
things.
fun. And this is, and these are all things that you can a youngster could purchase and work with?
No, this is going to be a teacher's going to do something like this because of 30% hydrogen peroxide. Take a look at the bottle. Move away. You've got a new suit. You know. So look at this. You can actually see the bottle getting warm. This is just a regular soda bottle, but you can start to see it. To see how it shrank just a little bit there? It's because it got so hot. So it really is a nice exothermic reaction. But I really think how that kind of works.
Cool.
That's fun. Never had one just take off that long before, so that's wonderful.
Oh,
yeah.
Well,
you're going to get a new suit because of the spot. Sorry about that.
You know,
yeah.
did you know that you had a hole in your sleeve? It's like, yeah, Steve Spangler knows I got a hole in my sleeve.
That's why we're never allowed to be together out in the public. It's just, this is what we do. Hey, there's a lot of stuff up on the website. We've got almost 400 experiments. The genie in the bottle is a hard one to recreate, but I have some other things that use some hydrogen peroxide that you can actually get in the store. Fair enough?
Okay, so that's our lesson for tonight, and tomorrow will be lesson 2. See you in school.